Good morning to one and all who gathered here for the virtual national conference on recent innovations in VLSI communication and signal processing RVCICS 2K21. This is my pleasure of introducing to you our beloved chief guest of today's conference. Sir completed his Bachelor of Engineering in Electronics and Communication Engineering from Karpagam College of Engineering from 2006 to 2010. Sir has completed his ME in Communication and Networking from Anna University, MIT campus from 2011 to 2013. Sir has obtained his PhD in ICE from Anna University, MIT campus from 2014 to 2019. Sir has 8 years
Good
of
morning
teaching
to one and all
experience and
who
he has
gathered here
completed
for the
9
virtual national
MOOC
conference
courses.
on
Sir
recent
has his
innovations
area of
in
interests
VLSI
in VLSI
communication and
design,
signal
digital
processing
signal processing, and
RVCICS
Internet of Things.
2K21.
Sir has received
This is my
patent
pleasure
in
of
Not
introducing
one
to you our
TOI of
beloved chief guest
IoT
of
enabled
today's
self
conference.
cleaning buoy for water
Sir
quality
completed his
monitoring.
Bachelor of
Sir
Engineering in
has record
Electronics
of
and
7
Communication
journal
Engineering
publications and
from
5
Karpagam
conference
College of
publications.
Engineering from
Also, here
2006
I
to
am happy to share
2010.
that Sir is
Sir has
also acting
completed
as
his ME
reviewer for
in
few of
Communication and
journals like
Networking from
Springer,
Anna
Journal of
University, MIT
Electrical
campus
Engineering
from
and Technology,
2011 to
and IET
2013.
Circuits,
Sir
Devices and
has
Systems.
obtained his
Sir has
PhD in
organized
ICE
5
from Anna
programs and
University,
participated in
MIT
56
campus
events
from
of seminars,
2014 to
workshops,
2019.
FDPs.
Sir
Also,
has 8
Sir has
years of
6
teaching
invited
experience
lectures.
and he has
It is with
completed
deep
9
pride and
MOOC
humility
courses.
that I
Sir
introduce the
has his area
keynote
of
speaker for
interest
this
in
conference,
VLSI design, digital
RIVCS
signal processing, and
2K21.
Internet of
I
Things.
heartily welcome our chief
Sir has
guest,
received
Dr.
patent
E.
in
Kongavail.
not
Sir
one
is
TOI
Senior
of
Assistant
IoT
Professor in
enabled
School
self
of
cleaning buoy
Electronics
for
Engineering
water
from
quality
Vellore
monitoring.
Institute of
Sir
Technology,
has
Vellore.
record of
Now,
7
I
journal
invite you to
publications
give
and 5
inaugural
conference
address, sir.
publications.
Thank you.
Also, here I am happy to share that Sir is also
Thank you,
acting
Baby
as
Prasanna.
reviewer
Our
for
chief
few
guest,
of
sir,
journals
profile
like
is an absolute
Springer,
motivation to all
Journal
of
of
us.
Electrical Engineering and
Now we have come to
Technology,
the most
and
awaited moment
IET
of today's
Circuits,
event.
Devices
I
and
heartfully
Systems.
invite our
Sir
guest
has
speaker to
organized
deliver the
5
chief guest
programs
address.
and participated in 50.
Topics. Again, it
Thank you, Baby
got an
Prasanna.
unprecedented
Our chief
increase.
guest, sir,
This conference
profile is an
aims to
absolute
bring
motivation
together
to all of
innovative
us.
academics,
Now
researchers,
we
and
have come to
industrial
the most
experts in the
awaited
field of
moment of today's
communication,
event.
signal
I
processing, and
heartfully
VLSI
invite
design
our
to a
guest
common
speaker
forum.
to
Predict the failures or predict the of a system or even if a motor like that based on the data, based on what data we have received, based on processing the data, we can predict at what time it will fail. Like that we can analyze from the data we have received. That is why we call Internet of Things has some intelligence. And we can view IoT in three convergence. One is things oriented visions, second one is internet oriented vision, third one is semantic oriented vision. So what are the components available in things oriented visions? Say an RFID, say an UID, or smart items, wireless sensors and actuators, and which is connected with internet oriented visions by connectivity for anything and communication things. So what is available in the internet oriented visions? We have IP for smart objects, internet of things, web of things, everything. What is there in the semantic oriented visions? We have reasoning over data, semantic technologies, semantic execution or the environments, like how a prediction can be done or what are the analysis can be done with the given data that fall under semantic oriented visions. So combining these three things, internet oriented vision, semantic oriented vision, things oriented vision, we call it is an internet of things. And how the interactions can be done. The interactions can be done between the digital world and real physical world. We call that as things integration. Real physical world with the virtual cyber world with the semantic integration, and the digital world virtual cyber world with data integration. So what are the three different integrations we have in Internet of Things? We have things integration, we have data integration, we have semantic integration. So coming to landscape, so it starts from wearables. So we have sports watch, we have Bluetooth watches that not only shows you the time, it can measure the heartbeat or the other things we are in need, and we can connect those wearables with the connected cars, then connected homes, connected cities, then the industrial sectors, industrial internet, transportation, oil and gas, healthcare, everything can be connected. So we can view the internet of things landscape in this manner. It starts from a wearable, it ends in the industrial applications for IoT. And so where we are using our IoT, we use our IoT in daily life, starting from alarm clock, which has remote programs, custom tones, turns on coffee makers, and coming to the next one, coffee makers, it has custom setting for each coffee type. Starts when alarm goes off, then smart scale which measures and sends weight info for progress tracking. Coming to the refrigerator, oven, automobile, VoIP phone, HVAC, vending machines, computers, printers. So everything we are going to connect. We are going to connect all the things we are going to use. So in our daily life, starting from the bed and ending in the bed, in between, what are all the things we can connect using the Internet of Things, which provide some useful information or useful data to the human beings. It starts from alarm clock, it ends at it ends at the bend. So starting from the television, we have a refrigerator, we have printer, microwave oven, coffee maker, everything we are going to connect in this IoT era. This is what the achievement or the IoT we are going to see in next few years. So how it is working? The nature of data is actually shifting. You see, in the year 2000, we have only internet and only one device. In 2010, we have multiple devices, more than two devices we have, and you see how much data we use per day. It is around 250 MB. And in 2015, the social platforms have come into the existence. We started using the social platforms, and we require more memory for them. I mean, more data for them. Then after 2017, everything is connected by using IoT, the drones, the gaming, VR, or again coming to the wearable devices, everything gets connected. So what is the need for this? So in the year 2000, you need only one device, but now we need more than four or more than five devices. We will see how the number of devices per person increases. You can see when comparing with the world population in the year 2003, number of connected devices per person is 0.08. That means not even a single person has a single connected device, not even one connected device. But in 2010 it is 1.84. So in the year 2007 or 2008, more connected devices than people. Our world population again it increases. So for the world population, it was 2003, it was 6.3 billion, and 2020 it is now 7.6 billion. So according to this data, the number of connected devices in the year 2003 was only 500 million, but in 2020 it is 50 billion. So number of devices gets increased. You can see connected devices per person in the year 2020, it is 6.58. That means each person has 6 connected devices. So what is the source for those devices? What is the source for those devices? We cannot concentrate only on connecting the devices. We need to concentrate on how to manufacture the efficient by term area efficient. That means size of the device, energy efficient. I mean the power consumption must be less, and high speed data transfer must also occur. We are not using the devices without connecting, as the term says it is the connectivity of things. We need high speed data transfer, we need less size. Similarly, we need low power consumption. So what we need an efficient VLSI design to manufacture these devices which we are going to connect with the Internet of Things. So coming to the trend, what we can see is, you can see the trend for the mobile phones keep on increasing. We know why. In the year 2010, we obviously may or may not have one mobile phone in our home, but now in the year 2021, we have at least for four people, we have at least five mobile phones. So the need for the devices which we are using for the mobile phones, it increases. And also you can see the you can see the consumer electronics trend. In the consumer electronic trend, it was less and now it was very high. The consumer electronics alone plays a major role in manufacturing the devices which we are going to utilize for the Internet of Things. So as we said, 50 billion devices are required. So how 50 billion devices are can be manufactured? It is not alone only we are going to manufacture the devices. We need efficient devices. Coming to the industrial internet, we can see the IoT again plays a major role in traffic systems, transport and logistics, utilities, smart grid, security and automotive. So the industrial internet, consumer electronics are also raised. But the devices which are required for the PCs and the fixed phones, which are stagnant, is not that much developed when comparing with consumer electronics and industrial IoTs. So what are the challenges we face in manufacturing these devices or developing these devices? We can categorize that into three categories: at end units, at servers, at communication. Why? Because when we are talking about Internet of Things, we cannot talk only about that particular device. We need to talk about the servers. We need to talk about the communication establishment between these devices. So coming to the end units, we start from power supply, which gives the energy, whether it is autonomous or non-autonomous, or the design for cost, design for power, design for hostile environment, like what happens when the device is connected in high noise or limited computation capability, limited bandwidth, or not standard interfaces to sensor and actuators. So that will lead to erroneous data that must be avoided. So these are the challenges at the end units. And at servers, again, whenever we are talking about servers, memory is a major part we are going to concentrate about. Then CPU and DSP, which is digital signal processing, and more. Again, in communication, wireless transceiver, metadata, or the security algorithms, we need to concentrate at the communication end. So how we can categorize these VLSI devices when we are into the Internet of Things? We can talk about the flexible electronics or flexible electrodes, nano biosensors, printed electronics, and these electronic devices, these electrodes, these sensors, actuators must be based on a proper silicon CMOS or VLSI or ASIC. That is why we are going to see the trends for this VLSI. So whenever we are talking about VLSI, we cannot omit the principle proposed by Gordon Moore, which states that number of transistors on an IC doubles approximately roughly every 2 years. So you can see the transistor count in 1970s per chip is actually some 5,000, and this in the year 2016 it was actually more than 10 billions. So the number of transistor count also matters here, because based on that only we can manufacture or we can develop a device. And whenever we are talking about the Moore's law, we need to talk about the technology scaling. So the technology scaling, what is meant by technology scaling? Technology scaling is nothing but when you are keep on reducing or keep on scaling the size of the device, we cannot have the same voltage, we cannot have the same supply, we cannot have the same electric field. So there comes three categories of technology scaling: constant field scaling, constant voltage scaling, general scaling. Like that, we have different types of scaling based on the proposals proposed by the technology scaling. We need to scale the devices. Just like that, we cannot reduce the size of the device. Just like that, we cannot reduce the power supply. So we need to have a standard. That those standards are provided by the technology. scaling. And the size of the devices, whenever we are talking about the size of an individual transistor, we need to talk about the size of the channel length. In 2000 or 2010 it was 130 nanometer, and now the many research articles are based on 10 nanometer technologies. And even now in 21 several researches are going on in 6 nanometer technology. You please imagine the size of channel length. If the channel length is 6 nanometer, say it is 10 nanometer, that is the length or the is size between the source and drain of a MOSFET. That is the size of the channel. So in that size, in that nanometer, or we can call it as an angstrom. So 1 angstrom. So in that 1 angstrom size, we have to create the substrate that can withstand the channel formation. That the channel will should withstand the flow of electrons or the flow of electric current between source and drain. So this is why we need technology scaling. So what are the issues we face in IoT developing a sensor? So what is the portability of the device? Whether the device can be portable or real-time analysis. So for how long the data will be sent to the server or sent to the cloud. Sensor correlation or security of data transfer. Whether the data you are going to transfer from the sensor to the cloud, whether it is safe, whether it is secured, we have to concentrate on that. Again, we cannot deal about the cost of the sensor, and accuracy and accurate validation are also the important things whenever we are talking about developing a sensor. Whether it is portable, whether it can give real-time data, whether the data transfer is secured. So if all these things are the advantages, we have to look about the cost of the sensor or accuracy of the sensor. So when we are looking into the worldwide investments, you can see the Korea invests in the year 2020. It is 18.31 billion. You can see the rapid increase in the investments towards semiconductor. This is nothing but semiconductor investments. You can see the Korea. It starts from the year 2016. It is only 7.69 US billion dollars. Now it is 8.31 billion dollars. And similarly, you can see that China from 6.46 from 17.06, and you can see Taiwan, it is actually stagnant. Japan, it is increased. North America, it is little bit increased, and Europe, it is somewhat increased. So the Korea and China, they are ready for taking these things in the IoT era. So they invest much things in these semiconductor manufacturing things. So now what are the real challenges for this VLSI for IoT? Ultra high speed. We need very high speed. Ultra high speed we require. Noise, crosstalk should be avoided, and reliability in different environments. How these devices are really reliable, withstand the environment. What about the power dissipation and clock distribution? What about the cost of fabrication? What about the cost of market? What are the time? What is the time taken for the fabrication, from fabrication to the market? What are the different challenges? That's what I said. Challenges in scaling reduce. That means reducing the size or reducing the voltage supply, reducing the power, reducing the field strength. Then get the cost per square centimeter, recyclability, degradability. So these are the different factors which we need to concentrate when we are developing these kind of sensors. So these things falls not under the IoT. These things fall under VLSI. And so in the future, what are the technologies that may drive these things? Nanomaterials and nanotechnology, sensors and networks, starting from artificial intelligence, robotics, digital manufacturing, biotechnology or bioinformatics. These fields we have to get inputs from different fields for the development of the sensors what we need. So for this, the VLSI needs to be reimagined. We cannot stick with the silicon. We cannot stick with the technology scaling proposed for silicon. So we need the VLSI to be reimagined. So how we can reimagine that low cost per unit area, even though it is available in pure VLSI, we need to talk about the low cost per unit area. And whenever we are talking about cost, we cannot talk cost in a general view. We have to talk the cost per unit area. Shrinking the package, VLSI on biodegradable, biocompatible, flexible substrates. Why here the bio term plays a major role means we are going to fix or we are going to fit the sensors or actuators in under the soil or above the soil wherever we need. For example, whenever we are talking about the agricultural IoT, we have to concentrate on these biodegradable or biocompatible substrates. So we cannot depend only on the silicon. What about the economics and cost? You can see cost per transistor. So per transistor in 130 nanometer it is one transistor, and now it is around 14 nanometer. Now even as I said in the year 2021, many articles are about 6 nanometer or 9 nanometer technologies. So we have to concentrate on the cost per transistor, not the cost per IC per transistor. So when you can see when the device size is reducing, so starting from 130 nanometer to 14 or 10 nanometer, you can see the cost per millimeter is increased. Right, it is around $4 per millimeter square. So reducing the size, that does not mean you are going to reduce the cost per transistor. Actually, the cost per transistor is raised. Similarly, per transistor, when you are going to see, it is $1 per transistor for 130 nanometer, and for 14 nanometer it is 0.1. This is per transistor and this is per millimeter square, because the packing the transistor in that particular area is the difficult task we are going to see in the VLSI design. And when we are looking into the revenue, you can see the in the 2022 semiconductor revenue, smart highest share semiconductor for manufacturing or for developing the smartphones. And from 2017 to 2022, whenever we are talking about the growth, industry and automotive shares the highest rate. So 21.2 percentage is 25.2 percentage in the billions. It is around 30 billions, and automotive is around 25 trillions. So how the trend is going towards? Trend is going towards automotive, industrial, and you can see the growth of smartphones is less. Total revenue in the smartphones is higher, but the growth is lesser when comparing with the automotive and industrial things. So here comes, we can have the use of application specific processors. What is meant by general purpose processor? General purpose, you take a scientific calculator, that is a general purpose computing. You can do anything. You take a microprocessor, that is a general purpose computing. And we are going for domain specific computing, like DSP processors. So DSP processors can do image processing, it can do signal processing, it can do video processing. It is domain, it is up to that domain. So the flexibility is a little raised when we are talking about general purpose and domain specific computing. The flexibility is little reduced, but performance, in terms of performance, it is increased. DSP has more performance than general purpose processors. Similarly, when you are going for application specific processor, you can see the flexibility is much reduced when comparing with the domain specific. Why? Because it is application specific. For example, we have the processor which is used for the washing machine. We cannot use the same processor for other than washing machine. It will do only the intended task. But what about the performance? Performance, it has more performance than domain specific computing. And in between we have a reconfigurable system. So the reconfigurable system means we are going to change, or the architecture can be adapted on the fly. So on the go we can reconfigure the systems for this particular kind of application. That is reconfigurable systems. That is another flexibility is reduced topic of performance. And now we are going to concentrate on the application specific computing. Why? Because it gives more performance with less flexibility. Because when you are going for application specific, we don't require actually the flexibility. We need a performance. So here comes the different things of application specific IoT, starting from Internet of Battlefield things. So what it can, what object it can give, what things it can give. It can give sensors, unions, weapons, vehicles, whatever we are required in battlefield. Similarly, Internet of medical things (IoMT), Internet of animal things, Internet of waste things. So for each subdomain, we have specific design challenges, specific optimization parameters, similarly specific objects. So based on that you select. So you don't go for a general purpose Internet of Things. You go for a specific, whether you are developing Internet of Things for battlefield things, you go specific. Or animal things, you go specific. In a similar way, we have different things. You can see Internet of underwater things, Internet of underground things, Internet of nano things, Internet of mobile things. Each one has its own objects, each one has its own design challenges and optimization parameters. So now, again, we have to revisit the challenges. So as I said, cost, power, and performance, speed are the major factors. So we can revisit challenges in three different categories, starting from hardware, sensors, data processing, system level. We will see hardware and sensors. So how is the device powered in order to function sustainably over the intended life? Power consumption. So how you can give the power? What about the power source? Whether the sensor system is reconfigurable. The calibration of sensor can be reconfigured to increase or decrease the precision or sensitivity. Similarly, how you can apply the machine learning model, right? Because as I said, we have to get inputs from artificial intelligence, right, for developing our sensor. So how this machine learning model can be updated if the sensor platform can communicate. And coming to data processing, how are variables sampled at different frequencies fused together? How to handle missing data? So if one of the sensor goes offline or becomes unreliable, it can cause missing data. How to handle the variations in data formats? So the sensors can be from different vendors, and different vendors may have different formats for the data. How you are going to handle, how to ensure data reliability, how to ensure the data security. These are the things whenever we are talking about the data processing. So for hardware or the sensors, we have different challenges. For data processing, we have different challenges. For system level also, we have different challenges. What about the machine learning models or the data sampling or the application of deep learning requires a large amount of data? So how we are going to handle these things? So here comes the reimagined VLSI for IoT. So finally, here are the concluding thoughts. So what are the technologies that leverage VLSI continue to ripen? Low cost VLSI is needed the hour. As I said, keep on decreasing the size. That does not give you a low cost material, rather the cost will be increased. And can VLSI reimagine itself and change the cost paradigm? Or can scaling in VLSI be a physical scaling? The scaling is actually not a physical scaling, but whether it can be a physical scaling. Can VLSI translate using flexible biodegradable substrates? These are the questions we need to ask ourselves as a VLSI engineer, as an IoT engineer. These are the references through which I have prepared these slides. And thank you. So finally, here are the concluding thoughts. So what are the technologies that leverage
Thank you, sir, for
VLSI
your
continue to
insightful and
rise?
visionary thoughts.
Low cost VLSI is
I
needed
w-
the
now,
hour. As I said,
now
keep
I
on
would like to
decreasing the
call
size. That does not give
R.
you a low
Haripriya,
cost
SP
material, rather
Haridharni,
the cost will
R.
be
Chitra,
increased.
Syed
And
K.
can
Namira
VLSI
Satya
reimagine
to
itself and
present.
change the cost paradigm? Or can scaling in VLSI be a physical scaling? The scaling is actually not a physical scaling, but whether it can be a physical scaling. Can VLSI translate? And can I take another 1 minute, ma'am? These are the questions
Yes, sir, sure,
we
sir.
need to ask ourselves as a so I must thank Dr. V. Kumari, ma'am, Professor and Head Department of ECE, for giving me this opportunity. And I thank Mr. E. Ramesh Marivendan, Assistant Professor, Department of ECE. Without him, I will not be here now. Thank you very much, sir. Thank you very much,
Thank you,
ma'am,
sir,
for
for your
giving me an
insightful
opportunity.
and visionary thoughts. Good morning to one and all present here. Myself, Haripriya R, a student of Avinasilingam Institute from Home Science and Higher Education for Women, and my co-authors are Mrs. Chitra R, a faculty member of Avinasilingam Institute, and Ms. Haridharni SV and Ms. Syed K. Namira Sadia. Our paper title is all about Fast Transistor and Transmission Gate, a comprehensive survey. Coming to the outline, Haridharni, next slide. These were all the contents which we are going to discuss in our upcoming slides. Next. Next is the abstract. A fast transistor logic is also known as a transmission logic gate, which is based on the use of MOSFETs as switch rather than as inverters. As we see, under intensive competition in the
Good
microprocessor,
morning to one and all present
microcontroller,
here.
ASCIIs, and
Myself,
related logic
Haripriya R,
marketplace,
a student of
the
Avinasilingam
differentiation and
Institute from
gaining
Home Science and
competitive
Higher Education
advantages
for
in
Women,
performance
and
and
my
cost is
co-authors are Mrs.
crucial for
Chitra
a chip
R, a faculty member of
to
Avinasilingam
survive. So,
Institute,
to gain such
and Ms.
advantages,
Haridharni
new
SV and
circuit
Ms. Syed
techniques
K.
which
Namira
go beyond this
Sadia.
conventional CMOS
Our paper
circuitry
title is
have
all
been
about
given a great
Fast
deal of
Transistor
attention.
and Transmission Gate, a
So, these will
comprehensive
include
survey.
the fast transistor
Coming to
based
the outline,
logics, and among these, an NMOS based fast transistor
Haridharni, next
circuit
slide.
have a great
These were all the
potential
contents
to
which we are going to discuss in
CMOS,
our upcoming
not only in
slides.
performance but also in power. So the fact that this NMOS fast
Next is
transistor
the abstract. A fast transistor logic
has
is
long
also
been
known as
an
a transmission logic
indispensable
gate, which
element
is
in the
based on the
memory
use of
cells of
MOSFETs
DRAM
as
and
switch rather
SRAM.
than as
When
inverters.
coming to a
As
transmission
we see,
gate, it
under
is an
intensive
analog gate
competition
similar
in the
to a relay
microprocessor,
that can conduct in
microcontroller,
both
ASCIIs, and
directions
related logic
by a
marketplace,
control signal with
the
almost
differentiation and
any
gaining
voltage
competitive
potential.
advantages
So
in
this
performance
CMOS
and
based
cost
switch in
is
which PMOS
crucial for
passes
a
a
chip
strong 1 but
to
poor
survive.
0,
So
whereas
to gain such
NMOS will pass
advantages,
strong
new
0 but
circuit
poor 1,
techniques which go
and
beyond
these
this
both
conventional CMOS
PMOS and NMOS
circuitry
will work
have been given a
simultaneously in
great
case of
deal of
transmission
attention.
gates.
So
Next
these
comes
will
the
include the
introduction.
fast transistor based logics, and among these, an NMOS based fast transistor circuit have
Haridwari,
a
next
great
slide.
potential to
Coming
CMOS,
to an
not
introduction
only in
about a
performance
transmission
but
gate. And
also the
transmission
fact
gate
that
is
this NMOS
basically
fast
made up of
transistor
two effect transistors where they are not
has
connected
long been
internally to the
an
source terminal of the gate.
indispensable
And these
element
two
in the memory
transistor
cells of
is
DRAM and
one is
SRAM.
N channel
When
MOSFET
coming
and
to
P
a
channel
transmission
MOSFET.
gate, it is an
MOSFET is
analog gate
nothing but a
similar to
metal
a relay
oxide, a
that can
semiconductor field
conduct
effect
in both
transistor.
directions
These both N
by a
channel and P
control
channel are
signal with
connected in
almost any
parallel.
voltage potential.
However, only the
So this
drain and the
CMOS
source
based
terminals
switch
of
in
these
which PMOS
two
passes a
transistors will
strong
be
1
connected
but poor
together.
0, whereas
Then will be connected
and
to
these
each
both
other by a NOT
PMOS and
gate, which
NMOS
is
will
known as
work
an inverter, to
simultaneously in
form the
case of
control
transmission.
terminal. Then the
Next
basic
comes the
building
introduction.
blocks of this data path structure is made up of flip-flops, and these data will be processed by combinational
Haridwani, next slide.
circuits, which will be stored, and
Coming
the
to an
operations
introduction
at a
about a
given clock
transmission gate.
frequency
A
will be
transmission gate
synchronized
is
using this flip-flops.
basically made up of two
The concern
effect
issue in the
transistors
evolution of the integrated
where they are
circuit
not
towards high
connected
frequency with
internally to the source
integrated
terminal of
density
the
of
gate.
power,
And
less
these two
speed, and minimum
transistor
delay with high
is one
speed.
is N-channel MOSFET and P-channel
This
MOSFET.
transmission
MOSFET
gate
is
and
nothing
pass
but a metal
transistor
oxide, a semiconductor field
will
effect
attempt to
transistor.
re-examine the
These
possibility
both N-channel and P-channel are
of their
connected in
uses in
parallel.
top-down
However,
approach,
only the
and
drain
this
and the source
top-down
terminals of
approach
these
includes entering the
will be connected to each other by a
game-based
NOT gate, which is
applications
known as an
because of the
inverter, to
necessity for
form the
various
control
design tools
terminal.
and libraries.
Then the basic building blocks
Next,
of this data path structures is made up of flip-flops, and these
next,
data will
what
be
is the pass
processed by
transistor?
combinational circuits,
This is
which will be
the
stored,
figure
and
represents
the
the
operations
circuit
at a
of a
given
pass
clock frequency
transistor.
will be synchronized using this
Here,
flip-flops. The concern issue in the evolution of
the
the
pass
integrated
transistor
circuit
logic
towards
is
high
one of the
frequency with
promising
integrated density
technologies
of power, less
which will
speed, and
improve the
minimal delay
power
with high
dissipation and the
speed.
circuit speed and also the area
So
of the
this
circuit.
transmission gate and pass
Then,
transistor will
however, the
attempt to
most
re-examine the
CAD
possibility
tools do not have appropriate
of
design
their
function for
uses
this
in
new pass
top-down
transistor
approach,
low power
and this
circuit
top-down
technology.
approach
Uh,
is entering the
then
game-based
The
applications
pass
because of the
transistor,
necessity for various
it is
design
based
tools
on the
and
use of
libraries.
MOSFETs as switches rather than as inverters. Then this pass transistor will describe the several logic
Next,
families
what is
used
the
in the
fast
design of
transistor?
integrated circuits, and it will also reduce the count of transistors